In this video, I want to convince you that the matrix that we found in the previous video that we claimed was the inverse matrix is in fact the inverse matrix. So I'm going to work with this general matrix here with A1, A2, A3 in the first row, B1, B2, B3 in the second row, etc. And I'm going to construct a matrix, and the claim is that that matrix is the inverse matrix. So think about what we did in the previous video. And this is the example from the previous video. This top left element here was the determinant that was formed by taking the top left element in M, deleting the elements in this column, deleting the elements in this row, and finding the determinant of the remaining matrix, and then making sure we use the correct sign. And we called this the cofactor. Well, using a more general notation, I'm going to say that the cofactor corresponding to the element lowercase a1 is the cofactor capital A1. So the cofactor corresponding to the element lowercase a2 is this here. And remember, this includes the sign, so this is the cofactor capital A2. So the matrix that we constructed in the previous video is equal to 1 over the determinant M multiplied by the cofactor A1, A2, A3, B1, B2, B3, C1, C2, C3, but remember we need to transpose this, so we're going to swap our rows and our columns. But we don't know that this is the inverse matrix, so we can't call it M inverse. I'm going to call it N, but the aim is to show that N, so show that N is in fact equal to M inverse. And how are we going to do that? Well, N equals M inverse if and only if M times N equals N times M is equal to the identity matrix. So this is what we want to show. So let's do that, and let's start by thinking about M times N. Well, this is equal to A1, A2, A3, B1, B2, B3, C1, C2, C3, multiplied by 1 over the determinant of M. And then remember we have this instruction here to transpose. So in the columns we have A1, A2, A3, B1, B2, B3, C1, C2, C3. And let's just start multiplying that out. Well, we can take the factor 1 over the determinant of M. And if we start multiplying this out, we do the first row by the first column. Our top left element is A1, A1 plus A2, A2 plus A3, A3. And you might want to pause the video here and try and find the remaining elements in this matrix that is multiplying M by N. Well, I did that already earlier, and we can see that we get this matrix here. So now we're going to think about what actually these elements end up being. And let's just write out the matrix M here, so we've got it to help us think what's going on here. So let's start with the top left element here, and let's think about what this is here. Well, this is the element A1 multiplied by the cofactor A1, which is the matrix determinant of the matrix formed when I eliminate the elements in this row and this column. And then A2 multiplied by the cofactor A2, which is negative the determinant of the elements B1, B3, C1, C3. And finally we have A3 multiplied by the cofactor A3, which is the determinant of the elements B1, B2, C1, C2. Well, notice all you have done there is expanded the determinant of m by the first row. So this element here in the top left is just the determinant of m. Okay, so now let's take another element. Let's take the middle element and let's think about what this is. So here we take b1 and multiply by the cofactor b1, which is just, and if we remember taking our matrix of signs, this is negative the determinant of the matrix a2, a3, c2, c3. And then we take the element b2, eliminate the elements in the same row and column, and multiply by the cofactor b2, which is just the determinant of the elements a1, a3, c1, c3. And then we take b3 and multiply by the cofactor capital B3, which is just the negative the determinant of the matrix a1, a2, c1, c2. And again, notice this is just calculating the determinant of m, but this time expanding by the middle row. So this middle element is also equal to the determinant of m. And by some similar logic, you should be able to see that the bottom right element here is just the determinant of m by expanding across the bottom row. Okay, so let's look at some other elements. And let's take this element here and think about what this is. So this is b1 multiplied by the cofactor a1. So let's think about what the cofactor a1 is the determinant of the matrix b2, b3, c2, c3. And then we have b2 multiplied by the cofactor a2. So that is the determinant of b1, b3, c1, c3. But remember, these are signed, so we need the negative sign here. So this is a subtract. And finally we have b3 multiplied by the cofactor a3. Well, that has a positive sign, and it's the determinant of b1, b2, c1, c2. So let's just expand out this determinant. So we get b1 multiplied by b2, c3, subtract c2, b3, subtract b2 multiplied by b1, c3, subtract c1, b3, add b3 multiplied by b1, c2, subtract c1, b2. And again, let's expand this out. So we get b1, b2, c3 minus b1, c2, b3 minus b1, b2, c3, add c1, b2, b3 plus b1, c2, b3, subtract c1, b2, b3. And if we look carefully, we can see the first term is b1, b2, c3, and then here we have negative b1, b2, c3. So these two terms cancel out. The second term is negative b1, c2, b3, and then here we have positive b1, c2, b3. So these two terms cancel out. And again, we can see that these final two terms cancel out. So this element here is in fact equal to 0. And if you repeat that calculation for the remaining 5 elements, you'll find that all of these are equal to 0. And I'm not going to do those calculations, you can do those yourself. But if you look carefully, you might start to see why. So if we go back to this calculation, we have b1 multiplied by b2 and c3, and c2 and b3. So we have 1 multiplied by the 2 and the 3's. Then we have a 2 multiplied by the 1 and the 3's. And then we have the 3 multiplied by the 1 and the 2. And we have the change of sign here with the negative. So everything ends up cancelling out. And that will happen in all those other calculations. So what does this mean? Well, what this means here is if we get m times n is equal to 1 over the determinant of m. And remember, this is presuming that the determinant of m is not equal to 0. is equal to the determinant of m 0, 0, 0, determinant of m 0, 0, 0, determinant of m, or taking a factor of the determinant of m, we can see that that is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, which is in fact the identity matrix as required. So what we have shown is we've shown that m times by n is equal to the identity matrix. However, that's not quite enough, because remember, we also need to show, and we haven't done this yet, is that n times m is also equal to the identity matrix, and then we can conclude that n is in fact the inverse of m. Okay, so this is doing n times m, and what we have here is we have them in the opposite order, so we've got n multiplied on the left. And we might want to go about multiplying out this matrix again. So firstly, we do have 1 over our determinant of m, and then our first row, we get small lowercase a1 times by the cofactor capital A1 plus lowercase b1 multiplied by the cofactor b1 plus lowercase c1 multiplied by the cofactor c1. Our second element, if we do rows times columns, is a2 multiplied by a1 plus b2 multiplied by b1 plus c2 multiplied by c1. And again, you might want to pause the video here and complete the elements in the rest of that matrix. Okay, and I've already done these below, so again we want to do a similar thing. We want to convince ourselves that all these diagonal matrices elements are equal to the determinant of m, and all the remaining elements are equal to 0, and then our conclusion will follow. Okay, so I'm going to have a look at this top left element, a1 plus b1 plus c1, and I'm just going to draw out my matrix M on the left hand side here, so we have it. And what have we got here? Well, we have a1 multiplied by the cofactor a1, which is the determinant of these remaining elements here. Then we have b1 multiplied by the determinant of these remaining elements here, but remembering this comes with a negative sign because of our matrix of signs, and we are taking the cofactor here. And then finally we have c1 multiplied by the determinant of those remaining elements with a positive sign. So all this is calculating the determinant of m by expanding by the first column. And as you know already, you can find the determinant of a matrix by expanding by any of the rows or any of the columns. Okay, so what about this middle element? Well, that is just expanding the matrix, the determinant of the matrix by the second column. And this one here is just expanding the matrix by the determinant of the third column. So those diagonal elements are all equal to the determinant of m. For very similar reasons, if you go ahead and calculate some of those elements that I have underlined in yellow, you'll conclude they are in fact all equal to 0. I'm not going to do that, but you might want to stop this video yourself and try that yourself. So we have, as before, we have that this is equal to 1 over the determinant of m, 0, 0, 0, determinant of m, 0, 0, 0, determinant of m, which, taking the factor of the determinant of m, gives us the identity matrix. So what have we concluded? We've concluded that if the determinant of m is not equal to 0, and so m inverse exists, then m multiplied by n is equal to n multiplied by m, which is equal to the identity matrix, where n is just 1 over the determinant of m multiplied by the cofactors a1, a2, a3, b1, b2, b3, c1, c2, c3, making sure we transpose this. If this is all true, then we end up getting that n is equal to m inverse, and actually this is definitely true the other way as well, because if this is equal to the inverse of m, then we must have that multiplying it by m gives us the identity matrix.